And we're live. So we are the active rocket stabilization and altitude control team here at California State University, Los Angeles. Here are my team members, Sean Liu, Francisco Medrano, Moises Perez, and Miguel Pichardo, with our faculty advisor, Dr. Nurullah Arslan, our sponsor, Eagle Rocketry. And here's my name, Alfonso. So we're going to move on to the next slide, which is the intro and background. And now Sean is going to tell us a little bit more about that.
For background material, we're sponsored by Eagle Rocketry. Our focus is stability and altitude control, which would be through fins and air brakes. And we're going to concentrate on the center of gravity and center of pressure for this project. So main objective is stability and altitude. We're going to achieve this through actuated fins, static fins, and air brakes. This is going to be for the Spaceport America competition, and our goal is to reach an apogee of 30,000 feet. And then next is project management.
So first we have the system overview. Here we have a scale model of the rocket. First we have the static fins to the left. In the middle we have the air brakes. And to the right we have the actuated fins. Next slide we have the requirements table where we have the subsystems, requirements, simulation software. First, we have the static fins, which provide initial stability, and we use ANSYS and OpenRocket. Next, we have actuated fins, which are used to torque the rocket and maintain vertical flight. And again, we use ANSYS and MATLAB Simulink. Next, rocket dynamic controls, which correct flight with PID controls to communicate with actuated fins. We use MATLAB Simulink. For the air brakes, they're used to decelerate the rocket to achieve target apogee. And for this, we use ANSYS and SolidWorks. Finally, we have altitude controls, which trigger air brakes to open and decelerate to attain target apogee. We use MATLAB Simulink. Then we have theme roles for active rocket and stabilization and altitude controls. First, we have the air brakes. For mechanical design engineer, we had Moises Perez. For avionics engineer, Sean Liu. For static fins and stability design, we had CFD engineer, Miguel Pichardo. And for actuated fins, we had mechanical design engineer and team lead, Alfonso Moises. For avionics engineer, we had Francisco Medrano. Next, technical details and actuated fins and rocket airframe control, Alfonso.
Okay, so the main objective of this subsystem is to maintain the vertical flight, assistant to ascension of final altitude, and some modeling of rocket dynamics. And as you can see, there are the components used. So just a quick brief overview. We used some aluminum 6061 T6 for the frame and square tubing. We used aluminum 7075 T6 for the rods connecting the actuator fins. The NACA airfoil carbon fiber fins are put together by the stainless steel ball bearings, and those are all powered by the servo motors. And now a quick video of how they actually work. So here you can see them moving from side to side, and that is how it will be correcting the flight as it's moving vertically. And now the actuated fins test verification. The main test here was that of the bending stress. So we had about 3.98 times 10 to the 8 pascals, and compared to ANSYS structural, which was a 4.82 times 10 to the 8. So there's a 28% difference. in the stress, and they gave us a factor of safety of about 0.91. Moving forward in the part of the rocket dynamics control, here's the rocket airframe, which basically shows the velocity, position, acceleration, and change in roll, pitch, and yaw. And again, this was done on MATLAB Simulink using block diagrams. But yeah, and then in the position, you can see the Y, it goes up to 9,244 meters or 30,000 feet. And this simulation also includes the input of drag as it's moving upward in its vertical flight. There's no change in roll, pitch, and yaw due to making this ideal and having no moments instilled in it. And now the estimated budget and pricing for the actuator fins. So here you can see the components used earlier. So some aluminum 7075, some 6061 for various other components. The specific MG996R metal gear torque motor. And yeah, it comes to a grand total of $189.36. So from here, we're going to move on to Francisco, which is going to talk more about the rocket dynamic controls.
Some of the goals of the rocket dynamic controls include the control of the rocket. For this dynamic control, we have a controller that takes in values from an IMU. Those values are then passed over to a servo motor. This is programmed in Python, and it uses a Raspberry Pi Zero and a MPU 6050 as the IMU sensor. We initially did a trade study to choose our parts. We had an option of 3 separate microcontrollers, the Arduino Nano, the Raspberry Pi Zero, and the STM32. There are some mandatory requirements for these microcontrollers. They have to be I2C compatible because that is the communication protocol that the MPU 6050 uses. As well, they all have to be battery operated because it's going to be in the rocket away from other sources of power besides its own battery. There are some attributes or categories that we are interested in. Price, GPIO slots, weight, and the processor. These attributes are given a particular weight, and then these weights are given a score, 1 being the lowest and 5 being the highest. In our case, the most important attributes are the price, the number or amount of GPIO slots, and the processor speed. In the end, the Raspberry Pi Zero was selected based on good price, many GPIO slots, and its processor speed. We also did another trade study on the servo motor selection. Again, there are some mandatory requirements. I put that it has to work within the operational voltage, and in our case, these microcontrollers operational voltage is 3.3 to 5 volts, and they all have to have about the same relative speed. Again, we give weights to the attributes. In our case, we have price, speed, weight as in physical weight, and torque, with torque being the most important. And ultimately, the MG995R was chosen. We also started to do a decision-making process on how or what steps the system has to take in order to achieve its results. We have a start. We want to check the IMU sensor to see if it's working. From there, if it is working, then we want to check the servo motor, have a little movement test, reset the position, and then just monitor the IMU. Once we are monitored the IMU, we decided to break it up into several cases. For example, positive yaw, positive pitch, positive yaw, negative pitch, negative yaw, negative pitch, and so forth. Here's a map on how these components come together. We have the MPU 6050 or the IMU, takes in values, passes them over to the Raspberry Pi Zero. The Raspberry Pi Zero reads these values and has a decision-making process. From there, it determines an output for the servo motor. And based on those values, they are read again through the IMU. Here on the bottom, we could see how the IMU is connected to the Raspberry Pi GPIO pins as well. No. So this is some testing and measurement of some angles that we did with the project. On the first image, we have the servo motor and it's laying horizontally. Behind that, we actually have the IMU sensor, and that's there in the second picture. Another thing that we are interested in is measuring the graphs, like how do these angles look besides reading it off the serial data set. So we started playing with this graph in order to get these values. And one thing that we are interested in as well is the angles. If you see, there was an initial spike to 20 degrees and then down to 25 degrees. And that's just the movement of the IMU. And what is circled in red is the unwanted noise that we don't want passing over to the servo motor. If the IMU is reading these values and then it reads a big spike 2-3 degrees, the servo motor will move as well too. One way we correct this is by implementing a Kalman filter. The next slide. And the Kalman filter is implemented in order to clean up the random noise that the IMU produces. It does this almost like as a guess. It tries to guess the next potential value. So right here on the left-hand side is the IMU laying flat on the table. And then as you can see around the 40th iteration mark, we get a spiking value from +6 to -6 degrees. This would make our servo motor move very fast or try to move very fast from negative to +6 degrees. But with the filter in green, we can see how that spike is mitigated, and as well as the other spikes down into the 60 iteration mark and further. We also do another movement test such that the red is the original movement and the green is the filtered value. And here we also try to see how the Kalman filter tries to clean up some of that data, especially in the 50th iteration mark where we have a red value and almost like a 90-degree. We want that to be smooth, and that's where the Kalman filter comes in as well. Next, Moises is going to talk about the air brakes.
Thank you. For the air brakes, the goal is to achieve target altitude, and the way this will be done is by reducing the speed of the rocket when we deploy the air brakes close to target altitude. When we deploy the air brake, drag forces will increase, and this is what's going to cause the rocket to decelerate and come to a complete stop. Next, please. So here we have a design for the air brake system. It's made of aluminum 6061T6. And some of the work that was done was the top and bottom plate. We reduce the material so that it causes less friction when the plates and the air brakes blades are opening. This will cause the motor to work less. And the way we will connect this system is with bolts, nuts, and screws. Manufacturing methods that we will use will be water jet and purchase parts, such as bolts, nuts, and screws. Next, we have a video. Here we could see the air brake system rotating 240 degrees in order to open. Then it would just do the same thing backwards, 240 degrees to close. Some verification and testing that was done was flow simulation and bending in the air brake blade, buckling in the connecting rod that we used to connect the air brake system to the rocket, shear in the air brake blade, and ball bearing in the connection for plates that includes top, bottom plate, and the air brake blades, shear tear out. Next, we have a table of results. Here we have parts, material, failure mode, margin of safety, and failure force. First, we have the air brake plates. In bending, we obtain a margin of safety of 0.5 when a force of 2,766.79 newtons was applied. Next, we have air brake blade. Again, with shear, we obtain a margin of safety of 0.5 when we apply 6,921.43 newtons of shear force. For the connecting rod in buckling, we obtain a margin of safety of 2.9 when 2,224 newtons was applied at the top and 894 newtons applied at the bottom. Finally, for the connecting plates, a ball bearing, we obtain a margin of safety of 1.84. And for tear out shear, we obtain 4.88 when we apply a shear force of 2,224 newtons. Next, we have estimated price for the air brakes assembly. We have the items, numbers of parts, cost per part, description, and what it will be used for. We have the Never Rest Classic 40 gear motor, connection rod, mouse spec distorted threaded flange lock nut, and mule spec distorted threaded flange lock nut. They're different sizes. That's why we have it twice. Finally, the steel plate for the body, and for a total of 143.60 cents. Next, we have Sean in altitude controls.
So for the basic goals of the altitude control is to develop a system, a feedback system to activate the motor. This motor in turn turns the gears 240 degrees, which activates the air brakes, inducing drag on the rocket, helping us reach our target altitude goal. And then I explain more on the next slide. This was the first conceptual design that I designed on MATLAB. It consists of the controller and the DC motor, which is now a stepper motor. The MPU 6050 would be attached to the controller. It would detect a drop, and then in turn would turn the stepper motor, activating the air brakes. So these are the final hardware parts used for testing the Python code. It consists of the Raspberry Pi Zero, the ULN2003, which is the stepper motor driver, and the stepper motor itself, which is the 28BYJ-48, and the same MPU 6050 used for the altitude controls. This is just a basic layout of how those components I previously mentioned are connected. It starts with the MPU 6050 accelerometer, which is connected to the Raspberry Pi. That connects to the ULN2003 stepper motor driver, which is then finally connected to the stepper motor itself. And all of that is powered by a 5-volt lithium-ion battery. This is the basic outline of how the decision-making process would be made in the programming. So when you start the program, it runs a check through the MPU 6050. If it's working, yes or no. If it's not, a red light would turn on and it would run check again. If it is working, the motor would rotate clockwise and counterclockwise, basically like a flight pre-check, similar to how commercial aircrafts do flight pre-checks before flight with the ailerons. So if this is working, the motor would retract, holding the air brakes on a closed position, getting ready for launch. So it's reading 0 acceleration, which means it's still getting ready for launch. So if it's not reading that, that means it would read a peak in deceleration, which means it's already gone through its flight and it is now reaching its apogee, and then in turn, the motor will rotate to its open position and lock. After that, the rocket should be going to a negative axis, negative x-axis, which means it's going back to the ground. It would detect that, and the motor would rotate again, bringing the air brakes back in for a safe landing, and then the program terminates. And then on the next slide is just a preview of the stepper motor initiating, but it only goes into the open position due to time constraints and resource constraints. And then Miguel's gonna show the static fins.
Okay, thank you. So for the static fins, our goals for this is to maintain the stability of the rocket during takeoff and to minimize any weather cocking effects during its flight path. To achieve this, there's two things we keep in mind: the stability caliber, which relates the stability of the rocket. We want this stability caliber to be greater than 1 but lower than 3. Anything lower than 1 implies an understabilized rocket, which we don't want, and anything higher than around 3 will imply an overstabilized rocket, which again is unideal. The other thing we need to keep in mind is the apogee. We want at least 30,000 feet or 9,144 meters to reach the competition guidelines. Next, please. So for the stability caliber, as I said before, this relates to the stability of the rocket. The stability caliber is a ratio between the distance from the center of gravity to the center of pressure and the diameter of the rocket. So the center of gravity is the point on the rocket where gravity acts, while the center of pressure is the point on the rocket where drag and lift forces act on the rocket. So by finding the distance between these 2 points and dividing it by the diameter of the rocket, we can find our stability caliber, which, as I said before, we want to be somewhere between 1 and 3. Next, please. So for the static fins, we decided on the clip delta shape. The reason we decided on this shape was because it had some of the lowest induced drag of any fin shape, and by having such a low induced drag, we can reach a high apogee. As you can see right there, it's 9,308 meters, which is well above our desired apogee. And the stability caliber with this shape and the dimensions we chose gave us a stability caliber of 2.1. We decided for the material to choose aluminum because this is a high-powered rocket, so we need a material that can withstand the velocities that it's going at. For the cross-section of the fin, we decided on airfoil. By choosing airfoil, this once again correlates with the drag. The shape of it will have low drag when compared to other cross-sectional shapes. So with all that in mind, we needed to keep in mind also the fin flutter. Fin flutter refers to the vibrations of the fin as air flows over it. As the air flows over it, the fins will vibrate, and at high speeds, there will be greater vibrations. These vibrations can become so great that the static fins may snap off the rocket. And we want to avoid that entirely, so we need to calculate the fin flutter velocity, which is the velocity at which our fins will snap off the rocket. By doing the calculations, we find that our fin flutter velocity is 802 meters per second for our given dimensions. And by applying a safety factor of 80%, we get a fin flutter velocity of 642 meters per second. Using OpenRocket, we determined that the max velocity that our rocket will reach is 594 meters per second, which is well below both the safety factor of 80% and the overall fin flutter velocity. Next, please. With all that in mind, this is our overall rocket analysis, incorporating both the including the air brakes, the actuated fins, and the static fins. Right here is a velocity vector map of our rocket going 300 meters per second. You can see the localized areas of the air brakes and the actuated fins on the left, and we can see all the vectors and how they play out around those areas. While on the top right, we can see the static fins, and once again, that's a localized area, so we can see how the velocity is around these significant points. At 300 meters per second, we're almost at Mach 1, and we determined that our drag forces was 3,733 newtons, while our drag coefficient was 0.0825. And these values are just important to keep in mind when we analyze the entirety of the rocket. Next, please. And right here we have the experimental testing. To do this experimental testing, we had to create a scale model. The scale model was used in the wind tunnel, which was courtesy of Dr. Kuo, who instructed us and allowed us to do some testing on here. Here on the left, we have the SolidWorks render of our scale rocket, and then on the right is the 3D printed rocket. As you can see right here, our rocket had a slight angle in the wind tunnel. So this angle needs to be kept in mind when referring to the analysis of the theoretical versus the experimental data points. Right here, we have the values for our scale rocket with the air brakes open. On the left side, we have the ANSYS Fluent results and all the different velocities. As you can see, the drag coefficient theoretically is relatively similar. The range is from 0.0495 to 0.0505, while the wind tunnel results have a much greater range, and it doesn't seem to match completely with our theoretical values. This discrepancy can possibly be attributed to the angle of attack, which, as you saw previously, was not 0. So that may be some sources of errors in our analysis. On the next slide is a graph showing our drag coefficient wind tunnel testing. Right here, you can see that the range for each velocity seems to tighten up as we increase the velocity. So that's just an interesting thing that the team noted for the trend of the graph. Next, we have the similar table, but this time for the drag forces of the rocket. We can see that the drag forces increases as the velocity increases. And similarly, the drag forces experimentally also increase. But once again, we have some discrepancy. Our drag forces don't align perfectly with the wind tunnel results. And again, we may attribute this to the angle of attack, which gave skewed data points. On the next slide is, once again, the drag force for the wind tunnel testing. And as we would imagine, velocity increases, drag forces increases, and that is the results of our wind tunnel testing. Next slide, please. Next, Alfonso will summarize our project.
All right, so for the conclusion, we were able to complete the mechanical design and do some structural analysis of both the actuator fins and air brakes. We also designed and tested the rocket dynamic and altitude controls with MATLAB Simulink, Python, and some physical hardware. We performed CFD, or Computational Fluid Dynamics, and experimental analysis through ANSYS Fluent and the Cal-STED-LA wind tunnel in order to find both the coefficient of drag and the drag force. All right, and so for acknowledgements, we have Dr. Nurullah Arslan, who was our senior design advisor, and he helped us with the technical presentations from week to week. Dr. Kuo for assisting us with the wind tunnel and donating his time to help us set up. We really appreciate that. Drs. Thorburn and Bachman, just for coordinating everything in the senior design project department. Jonathan Cervantes for everything he did in terms of helping us with the scaled rocket, 3D printing it, setting it up. We really appreciate that. Eagle Rocketry, our sponsor, for giving us this great project to work on, and Cal-STED-LA Engineering, Computer Science, and Technology Department. And so this concludes our presentation. Thank you for watching.